How's it going? Something's happening to people on this side of the class. All right. Any last questions, worries, concerns about PA5, about the lab, about stuff? Yeah.
So we're trying to pass like a variable into sed as part of the regular expression. How would you do that?
Just $ variable name.
That wasn't seeming to work.
Were you getting tripped up by \r's maybe?
No, I don't think so.
So where were you trying to use a variable instead?
Well, we were
Like
just
it's part of
doing-
the program?
We were just doing it on the command line to test
Okay.
to see how it would work.
But where inside the sed statement?
We do like an s/$ variable name.
Ah, okay. So you can't use single quotes though, which I usually use with sed.
All
Right? So single quotes suppress the evaluation of $ as saying, give me the value of a variable. But if you use double quotes, right, $x will get replaced by the shell with whatever the value of x is. And so this becomes substitute hello with bye. You just have to be careful because if you want to use an anchor with a $, right, that's going to potentially get strange. So you may have to put together combinations of double quotes and single quotes, and it can get interesting.
right.
But in general, it should work like that. Actually, the anchors don't seem to trip it up in that case. Other stuff? So everybody should have had something for a few weeks now on Canvas asking you to do a teacher evaluation online. How many people have done that? Okay, cool. Make sure you do that before whatever the deadline is, which I think is probably another week or something. It's really important to do those, okay, because that's a big part of how Clark decides, you know, which teachers to keep and tries to make sure that you have quality teachers that are being effective and so on. So it's one of your most direct inputs into that whole process, right? And if you want to have a say in, you know, who's teaching courses that you're taking, it's a really good way to do it. Okay, and those reviews are taken extremely seriously. So definitely appreciate spending the time on those. Yeah.
I have a question about the grading on PA5.
Okay.
There's a lot of specifics that aren't really in the assignment itself.
Right.
Are those going to be like, you know, checking to make sure that the arrival date is after the departure date?
Optional.
Optional.
Yeah. So the bare minimum that I'm looking for is written in Bash, right? Uses entity. So it puts up dialog boxes, right? Somehow gets your name, departure and arrival date, departure and arrival cities, how many bags you want, and does the proper thing with the reservations.txt file, right? Adds a reservation, make sure that if somebody's in there, it replaces the record instead of making 2 records. And that's all I'm requiring. Okay, so everything else is sort of free creative expression. If somebody puts in 2.5 bags, that's their problem. Right? You can record that as 2.5 bags. You can say that's an invalid answer. If they say haha bags, you can say that's an invalid answer, or you can record haha bags, right? I'm not looking for anything in particular on that, but my hope is that you'll spend some time sort of playing around with possibilities, right? But yeah, it's pretty generous. And we usually see a lot of variation in what people come up with, so that's part of the fun of it. All right, no other questions? All right, I don't think we started talking about the exec function yet. Is that true?
Brought it a little bit.
So did we say anything about this yesterday? How far did we get? Or what did I say about it?
Replace the code for.
Okay, so we talked about the basic behavior of it, right? So we can put in a program name and some other arguments. And this replaces your current program memory with the contents of that executable file, right? So it basically turns you into someone else. Did we play with any code with this yet? Okay. All right, so here's 3-line test program. We'll say here we go, we'll execute the exec function with bin date. Second argument, I always just do quote, quote. That's like the command line argument list, and the third argument is supposed to be null. So I don't know why they require it, but they do. And then we'll just print out a message saying that we did exec. So we'll go ahead and execute this program. And it says, here we go, and it shows us the results of running the date command, and it didn't do that final print. And why didn't it do the final print? Exactly. These print statements are no longer part of the program memory after we do the exec. When we do the exec command, program memory is replaced with the contents of bin date. And so that's the program that's executing now. And this stuff is gone from memory. It's not part of our execution stream anymore. So we're not just running the date function, we're becoming the date function. Okay, slight difference, but significant. So let's use a fork. And if fork returns 0, we know we're the child process, so we're going to do the bin date, and we're going to print a message saying that was fun. Otherwise, we're the parent here. And we'll just print a message saying that the parent is finishing up. And now if we run this, says here we go, and then it says parent is finished, and it actually came back to bash and printed out our bash prompt. And then a little while later, we got the output of the date command. So this output here came from the result of this forked branch turning into the date function, right? But executing the date function, which doesn't do the print because the print's gone. But the original branch, right, skipped over this if statement because fork returned something non-zero, did its print, exited, and when that program exits, bash prints out its prompt and waits for input. And then a little while after that, the child process actually generated its output. So we're seeing something intriguing here, which is asynchronicity. Okay, when you deal with multiple processes, generally things are not synchronized. And in this case, the child process ran after the parent process exited. And that may happen more often than not. I probably can't get it to not happen. But if my CPU is busy, that might change things. So it's fairly consistent in this case, but it doesn't have to be, right? It could be that something else will happen. And certainly, if we do something like this, right, if the parent has other things to do, then the child process will do its thing and generate its output before the parent finishes. So when you deal with multiple threads, right, multiple processes, it becomes partially your responsibility to just figure out how things are synchronized. And that's going to be something we'll talk a fair amount about in spring in 223, because we'll deal with multi-threaded programs. And we'll talk about some of the pitfalls that can arise from this kind of asynchronous behavior. And some of them are pretty subtle. And some of them have the wonderful feature that your code may work fine for a few hours or a few days or a few weeks and then all of a sudden break because just the right combination of things and the right set of timings came together and exposed a bug that you didn't know about. And that's really fun because you write a server and it's running fine, but every like 3 to 5 days it just like crashes for some reason. And that's a real fun thing to try to debug because you don't have a nice test case. You can just go into GDB and say, okay, here's the code, right? And this is like when you play with interrupts in 270, when you do the interrupt lab. Works fine most of the time, but every now and then it just doesn't work for some reason, right? And it's because things aren't synchronized. The flipping of the switches isn't synchronized with the running of the code, and so things can happen in different orders and stuff. All right, so exec is this way that we can change our identity and become a different process. And when I exec into bin date generates output to standard out, and it came to the same standard out that we had in our original process, right? The new process shares the same file descriptor that's standard out, so it comes to the screen. So if I run E1 and I redirect the output into a file, what's going to happen? It's semi-rhetorical because I'm not 100% sure. But I think everything is going to go into the file. Well, we got something weird here. It gave the date before it said, here we go. And our main program clearly says, first we're going to print out, here we go, and then we're going to make a fork, and one branch is going to print the date, and the other branch is going to sleep and say parent is finished. But when we look at the output file, the first thing we see in there is the date. And then we see, here we go, and then we see parent is finished. Is that weird? That's pretty weird. So any quick ideas what's happening here? It is something we've talked about, but we've talked about so much at this point. This has to do with buffered output. The main program says, here we go, but because output is buffered, that doesn't actually go into the output file at the end of that print statement. It goes into a holding area, right? Because we like to push things to disk all at once. So we say, here we go, those words go into a holding area. And then we make a new fork, and that fork executes the date command, and the date command generates this date stamp. And that goes into a holding area, but it's a different holding area because it's associated with a new process. And then the date command exits, and when it exits, the stuff that it printed out that's being buffered up gets pushed out. So now the date command's output actually goes into the output file, and the parent is sleeping, and then it says parent is finished, and that goes into the parent's holding area. And then the parent process exits, so now its contents of the holding area goes into the output file, and so we see, here we go, and parent is finished. Again, asynchronicity, buffered output, all these things can be nice features, but they can make things really confusing. And this can drive you crazy at 3 a.m. trying to figure out what's going on. So stuff to look forward to. It's actually really fun playing with multiple threads, though, because it's just like it's this much richer space, and the things you can do with that are pretty fun to mess around with. All right, so we can execute commands by changing into a new command, basically, right? And so we played with popen yesterday. And I think we used popen to run the date command and to run the ls command, and we pulled input in from those and saw the results of it, right? So let's just go the other direction. So let's make a temporary array. And we're going to do a popen on BC, that's the calculator program. We're going to open it for writing, so it's going to listen to us. And then we're going to say print fprintf into that file descriptor. And then we'll close the file descriptor. So if we run this, we're creating a new process, BC. We're feeding into its standard in using that fprintf. And BC standard out is whatever the standard out was when we ran E2, which is just our display. And so we're seeing the output from BC, which is 2 plus 3 and whatever that multiplication is, right? So, so we can use popens for two things. We can run a command and say I want to grab whatever that command generates, which we did with the date command yesterday, or the ls command. Or we can run a command and we can say, I want to supply the input for this command, right? I want to feed standard in by pushing things into this file pointer. But it would be really useful if we could do both. If we could send to standard in and read from standard out of some remote command, right? So system, you can't do either. You say system command, it just goes ahead and runs that command. If you do fork and execl, you change into that command, your original program basically disappears, right? When you do execl, your child process becomes that new program. If you do P opens, you can do one-way communication. You can write into standard in, you can read from standard out. We want to do both, so we need a couple of new functions. So the first is the pipe function. So pipe expects an argument which is an array of 2 integers. And what is a pipe? It's this, well, virtual pipeline. And information flows in only one direction in a pipe. So it's got an input side and it's got an output side. Okay, and it's a virtual construct. There's stuff that happens in the operating system to make it look as if what you put into one side of this pipe appears on the other side of the pipe. So the pipe function call creates a pipe, and we need a way to access these 2 ends of the pipe, know which side to write into and which side to read from. Okay, so this is what this argument P does. We pass it an array of 2 integers, and it gives values to the 2 elements in that array. And element 0 gets assigned a file descriptor that corresponds to this end of the pipe, the output side. And element 1 gets assigned a file descriptor that gets associated with the input side. So once we create a pipe, we basically write into element 1, and then if we read from element 0, we'll see whatever went into the pipe. So we need an integer array of 2 elements. So we'll call the pipe function that creates a pipe, and it will fill in the 2 elements of my pipe to tell me how to get to each end. So let's write into the pipe. So we'll write into my pipe bracket 1. Let's write the word hello. Let's write 5 bytes. And then let's read from the pipe. And we need a character array. So we'll call the read function. We'll say we want to read from the file descriptor, which is my pipe 0. That's the output side of the pipe. We'll load into this character array called temp, and we're going to ask to read 5 bytes. And let's take a look at the return value from pipe. Actually, let's go ahead and look at the one from read also. That's how many bytes we want to read. So if you look at the manual page for read, first argument's file descriptor, next is an array of characters, and the last argument is the count. All right, and then we'll just do a for loop, and we'll print out the elements in the temp array. So what are we doing here? We're creating a pipeline. We're pushing the word HELLO into one end, and then we're going to read 5 bytes from the other end, and we should get back HELLO, right? And it's a whole lot more marvelous than it sounds. Yes. Thank you. All right, so we run this, and the write command returned the number 5, the read command returned the number 5, and the first 5 bytes in our array are HELLO. So that looks fairly good. Let's print out 10 bytes of our array. Oh, boo. I was hoping it would be more interesting than that. All right, that's a little more interesting. So there's gibberish beyond the 5th entry in our array, right? Those question marks are negative numbers probably. And the others might be nulls or spaces or something unprintable. But the first 5 locations in that array are filled with the first 5 things we pulled out of the pipeline. Now, if I change my read statement and I say, let's just read 1 byte. Well, the first entry in that array is the first byte that was sitting there, which was an H. And everything after that, no idea what's in there. Right? We basically haven't touched it. So when you write into one end of a pipe, you're sort of pushing in these characters, and they're kind of queuing up. We pushed in 5 characters, HELLO, they're sitting there. And when we say read, we just start pulling off these characters, and we can tell it how many characters we want to read. That's how many things it consumes from the pipe. Okay, this is analogous to what's happening when you type on your keyboard and then you call getChar or fgetC and read 1 character at a time. You might have typed 50 characters, and they're all sort of sitting in this pipeline, and each time you get another character, it just pulls off 1 character, right? So what if we try to read 10 characters from the pipeline, and we're only writing in 5? Right, not a problem.
Where's the U?
We read, and it says, I've got 5 characters available for you. That's what the return from read says. And so it filled in the first 5 elements of the array, and it didn't touch those last elements, including the U. It just happened to be there. If I run this again, something else may happen to be there, like a T. So we asked for 10 characters, but read always returns to you a number which says how many characters did it actually read. And so it read 5. We know that the first 5 elements in our array came from the pipe, but everything after that we really want to ignore. And if we don't write anything into the pipe, well, write gives us some weird number. Oh, we didn't get a value from write because we didn't call status. So here we're trying to read from the pipe, and it didn't come back. It's waiting, right, for something to be available. So if we write 1 character, read will come back right away and say, hey, I read 1 character. But if the pipe's empty, read may or may not come back right away and say, I read 0. It depends on your installation. It depends on what you're actually reading from. Okay, this is another area where things can change. Right? Reads and writes, we're down at sort of the system level. Right? These are chapter 2 commands. This is why we usually do things from chapter 3, fgets, printf, things like that, because those are fairly well managed for us. And all of these subtleties kind of like get taken care of. So reads and writes can be a little quirky sometimes. So also be careful of this. I'm going to print out the contents of temp using a good old printf. And it told me temp equals hello with a question mark, even though I wrote hello into it, right? Why? Because I didn't write a null terminator. At the level of reads and writes, strings are just character arrays. Null terminators, new lines are completely, there's no special treatment around those, right? So if I write HELLO and I say write 5 bytes, it writes HELLO. And if I ask to read 10 bytes, it reads as many bytes as are available, which are 5. So it filled the first 5 elements of temp, but there was not a null terminator sitting after that. There might have been, it's totally random. Right, if I run this again, temp's equal to hello 2. So that can be quirky. All right, so we can create pipelines. And using these pipelines, we can have this virtual structure that we can write into one end and we can read from the other end, which by itself might be kind of fun, but doesn't really do a whole lot for us in terms of running commands and being able to send things to them and read things from them. So we got one other function we want to talk about, which is dupe2. And what dupe2 does is it lets us manipulate file descriptors. It lets us take a file descriptor and associate it with a particular new file descriptor. Okay, so these file descriptors are integers, right? And there's 3 file descriptors we always have access to. Standard in is 0, standard out is 1, standard error is 2. So if I say dupe2 some file descriptor comma 0, what I'm doing is reassigning standard in. So this says reassign standard in to whatever that file descriptor is. So dupe2 file descriptor comma 0. After that, if I try to read from standard in, I'm actually going to read from whatever that file descriptor was. Well, guess what? If I make that file descriptor the output side of a pipe, whoever's controlling the input side of that pipe now controls my standard in. And so if a process writes into that other end of the pipe, they're basically feeding what my process is going to read when it looks at standard in. And this is how we can connect commands together. So here's the whole program. So we've got our main branch coming along. We're going to make a pipe, which looks like this. So one direction of flow. Here's element 0, here's element 1. then we're going to do a fork. Which creates a new branch. And on the child branch, we're going to do a dupe2. And we're going to dupe to p bracket 0, 0. When we say dupe 2, standard in is now coming from here. And now we can say execl. And we can become another process. But as that process executes, anytime it tries to read from standard in, it's actually reading from this end of the pipe. And so our main process can write into this end of the pipe and feed what this child process is reading from standard in. So this is one directional, right? Yeah.
For that, do you need to initiate a delay somewhere in there to make sure that whatever you type on the parent process is always going to, so that the child process is not trying to read from standard in before the parent process?
Doesn't matter. Just like if it tries to read from your keyboard before you type, it'll usually sit there and wait. So if it starts reading from the parent process, and the parent process hasn't pushed anything into the pipe, it's basically just going to say there's nothing available in standard in yet.
So there's no way that you can accidentally load too much into standard in or something like that?
Theoretically, you can overflow the pipeline, but practically, no. Just like if you're doing an fgets, it doesn't actually ingest what you've typed until you hit an enter. So if you typed 100 billion characters before you hit enter, something might overflow, but in practical terms, probably not.
Okay. Thank you.
Yeah. So if we want to read from standard out at the same time, we basically create another pipeline. So we'll also do a pipe. And I should not be calling these P and Q, I should be calling them something more meaningful, but I'm going to call them P and Q. So Q is another pipeline, right? We input into Q1, we output from Q0. And so we're going to use another dupe2 command, which says take Q bracket 1 and make that file descriptor 1. File descriptor 1 is standard out. And so standard out is now this end of this Q pipe. And our main process can read from Q bracket 0. And now our main process has complete control over the input and output of this child process. Anything that the main program writes into P bracket 1 goes into standard in, and anything that it reads from Q bracket 0 is coming from standard out. So we could have that child exec some function, like BC, for example, the calculator, and if the parent writes into P1, that'll be the input to BC, it'll do some calculation, it'll print the output on standard out, which the main program can read from Q bracket 0. So instead of P, I'm going to call this write pipes. And instead instead of Q, I'm going to call this read pipes. And when you're doing code like this, you always need to sort of fix your reference point. What's your perspective, right? So my perspective when I came up with these variable names was from the point of view of the main program, right? Because the main program is writing into here, it's reading from here. It's the exact opposite for the child. From the child's perspective, it's reading from here and it's writing into here, right? And if you don't pin down that perspective early, it'll just flip back and forth on you until you go crazy. And you delete your code and start over. So it helps to fix your perspective. Okay, so let's look at some code. So I got a pair of pipe arrays, read pipes and write pipes. I've got a temporary string called buffer. I create my pair of pipes with 2 calls to pipe. And then I make a fork. Okay, and a fork returns 0. It means I'm the child process. So this is all code being executed by the child. So I duplicate write pipe 0 with 0, right? That's this call up here. So I take this end of the write pipe and I associate that with standard in. And I'm going to take read pipes 1 and associate that with standard out, which is 1. So I'll dupe 2 read pipes bracket 1 with 1 and write pipes bracket 0 with 0. This is the most confusing part of the whole thing, right? And I'm not going to get bogged down in details here, but you got a 1 in 4 chance of getting it right. Better if you draw pictures and have done it before. But this should work. Okay, so this is associating the child processes standard in, standard out with the appropriate ends of those pipes, and then it executes bin bash. So it's turning into a bash program. And then there's the existential angst of why am I here? That should never print, right? Because once that execl happens, you're no longer this piece of code. So if you get to that printf statement, something happened, something bad. So we'll print that out and we'll just exit at that point. But theoretically, you never get to that print. Replaces your current program memory with the program that's specified in the first argument. So it'll turn the child into bash. So down here, this must be parent code because fork did not return 0. So we write into the input side of write pipes, right? So we're writing into write pipes bracket 1, that's over here. And we're going to write date, new line, ps-l, new line, and if you count those up, that's 11 characters. So we'll write 11 bytes. And then we'll just go into a while loop, which basically reads from the read end 1 character at a time and prints out the character. And so this is a pretty limited main program. It just pushes 2 commands out and then just reads from bash, right? But it's still pretty marvelous. All right, so we'll go ahead and run this. So there's the date, there's the result of PS, right? This was printed by the main program using bash as kind of a slave process that it can send information to, and bash will respond accordingly and write back. So what does this PS show us? Well, the first line, bash, that's our original bash shell. Okay, that's the one we've been running this whole class. Process ID 743 created a new process called full bash. That's what happened when we said full bash right up here. So that's our main program. It forked, it execled into another bash shell, so we don't have 2 copies of full bash. Right, that second full bash after the fork turned into bash. Right, the parent was full bash 873, and then that bash command 874 created a new process PS 876. And if I suspend that, right, all of that is still going on. Nothing's exited yet. The status of bash changed from wait to pipe underscore wait, whatever that means. but everything is still sitting there. So if I Control-C my main program, then the process that it created goes away. And I'm back to my original state. So we could make this a little more useful. We could put a loop around all of this in some way. So we could write a command around this. So we could write a command into bash and then read the output of that. And then write another command into bash, read the output of that. Write another command, read the output, and so on. And now we could have a function called, do bash or something. We could just pass it a string. It would go ahead and execute that in a bash shell, take the results, send it back to us as another string. But there's one trick here, which is how much stuff should we read from bash's standard out? We need to read more than one character, so we want it in some kind of loop. Should we read everything up to a new line? Well, maybe if it's only generating one line of output, but if we're doing something like PS that generated 4 lines of output, we'd need to read 4 lines. And so how do we know how much stuff we should read? Well, we don't. Right? In this case, we don't know how much output's going to be generated. If we say ls, who knows how many lines it would produce? Depends how many files it's listing. So to make this really useful, we still want another pair of processes for the main program. One which lets us take a command and send it to the child process, which is running bash, and another that reads whatever that child process is sending to its standard out and prints that out or captures it or does whatever we want to do with it. But it's the same problem I mentioned yesterday with the chat program, right? If we do a write read and we make a loop like this, then we're forcing these things to happen in lockstep. So we really want a pair of processes over here. One that's writing whatever we want to write to bash, and another one that's continually reading and displaying on standard out. So we'd probably make another fork over here. And one of these would handle output, and one of these would handle input. And so it can start getting more and more complex. None of which you have to worry about too much for this course. But that's just kind of an idea of how processes come into being, how they get controlled. And this is how pipes work when you say, ls pipe into WC. Right? This is basically what bash is doing for you. It's setting up a pair of pipes. Well, it's setting up one pipe in that case. Duplicating the file descriptors, making a fork, running the WC command, making another fork, running the ls command. And it's set them up so the output of ls is the input of WC. And then when all that finishes, bash comes back and gives you a prompt. Says what now. All right, so tomorrow we'll start PA5 presentations. Guessing it'll take us 1 to 2 classes to get through them, depending how many people show up. So we'll do those, and then we'll say a few more things about processes. We'll talk about code profiling, and that'll probably take us into doing review next week. So I'll see you next time.